Okay, we are going to be talking about two related topics today. The first of which is source transformation. So this might seem unrelated at first, but we are going to very briefly review the concept of electrical equivalence, which is something that we've been dealing with for quite some time in this class. And we're going to start by looking at just a couple of simple examples. Okay, so let's say that I have the following circuit where I have some source voltage Vs connected to a network which contains two resistors in series. Let's call this R1 and R2 like so. I'm going to call the voltage drop across my two resistors VL for my load voltage, and I'm going to call the current flowing through my two series resistor IL for load current. Okay, so an electrically equivalent circuit to this would be the following. We have that same voltage Vs connected to a new network containing a single resistance. Req is equal to R1 plus R2, where we would have the exact same load voltage and the exact same load current flowing through the network that is connected to our source. So these are electrically equivalent circuits, right? We have already seen this by combining resistances. We could do something similar, putting resistors in parallel, voltage sources in series, current sources in parallel, etc. Okay. The rules that I'm trying to establish here for the concept of electrical equivalence is things are going to be or behave exactly the same. So our source effectively cannot tell the difference between two resistors in series or a single resistor that is a combination of the two, as long as the voltage drop over the network is the same and the current flowing through the connected network is the same. So now I want to show you guys something. Okay. I argue that the following two networks are electrically equivalent. And so I'm going to make a point here to give myself some load resistance on both sides. So we're just going to call this RL, such that there is some voltage VL over it and some current IL flowing through it. And the same thing on this side. And so what we're going to do is we are going to effectively explore under what conditions these two networks are electrically equivalent. But the first thing that I want to do is introduce a new term to you guys. So this guy on the left will be what we're going to call a practical voltage source. We call it a practical voltage source because it is modeling how real voltage sources behave. So to this point, we've said that any DC voltage source can be labeled or modeled with an ideal independent voltage source. Now, there is a slight problem with that. An ideal independent voltage source is capable of pushing out an infinite amount of current, regardless of what the voltage drop across its terminals is, okay? A real voltage source cannot provide infinite current. It can only provide some finite amount. The purpose of that resistor RS in series with our ideal independent voltage source is to limit the current to some finite value, okay? So typical values for the source resistance of a voltage source are somewhere in the ballpark of milliohms, usually, up to single-digit ohms if you have a very inefficient source. So like the batteries and stuff like that that you buy might have somewhere in the ballpark of half an ohm of resistance. Very high-end power supplies probably have single-digit milliohms of internal resistance. Okay. Then over here on the left, we have what we're going to call a practical current source, where this is nothing more than an ideal current source in parallel with some internal source resistance, RS. All right, so let's talk about under what conditions these two models are electrically equivalent, effectively saying that the load resistor RL couldn't distinguish whether it was connected to a practical voltage source or a practical current source. Okay. So if we solve for the quantity IL in the left-hand circuit, using whatever circuit analysis technique we choose, what might we find? So what's the easiest way to figure out what IL is? V over R. Sure, Ohm's law. Vs divided by RS plus RL. Perfectly reasonable, simple application of Ohm's law. Anybody have any problem with that whatsoever? All right. So let's look on the right-hand side. If we wanted to find IL, how might we do that? What was that, John? Current division. Absolutely correct. I would argue current division is our easiest option here. So that's going to look like IS times 1 over RL divided by 1 over RS plus 1 over RL. I'm going to do a little bit of manipulation here. So what I'm going to do is I'm going to multiply this numerator by RS over RS. I'm going to multiply this guy by RL over RL, this guy by RS over RS, and we can see that we have a common factor of RL times RS in the denominator of all of those terms. All of those are going to go away. And we will be left with IS, actually, let me write it like this. IS times RS over RS plus RL. Anybody have any problems with the amount of algebra that went on there? Hopefully fairly straightforward. All right, so here's the $1 million question. Under what condition is IL on the left-hand side equal to IL on the right-hand side? Thank you. No, shit. Is it Ethan? But you go by Tyler. Okay, sorry about that. Sorry for throwing both at you. Tyler. All right, so what Tyler suggested is absolutely correct. These IL on will be equal on both sides under the constraint that VS is equal to IS times RS, okay? Now we could go through and we could do something very similar here to find VL on both sides. We could use voltage division on the left-hand side, Ohm's law on the right-hand side, and we would find that once again, VL on the left would be equal to VL on the right under the condition that VS is equal to IS times RS. So this is the constraint that forces these two circuits to be electrically equivalent, okay? So effectively, what that means is that anytime we have a practical voltage source, we can convert it into a practical current source and vice versa. So let's say that we had a 6-volt source in series with a 3-ohm resistor. Anytime we saw that, if we needed to, for whatever reason, we could replace it with a 6 volts divided by 3 ohms or 2 amp source in parallel with that same 3 ohm resistor. Okay. Now I want to point something out here because it's an easy thing to miss. The polarity of the voltage source and the direction of the current source are related to each other. Okay. So the positive polarity terminal of the voltage source will be where the head of the arrow for the current source goes. So just to hopefully make this even more clear, if we had a 4 amp current source direction down connected in parallel to a 5 ohm resistor like so, we could, if we wanted to, for whatever reason, and we'll talk about that in a moment, replace this network with a voltage source that would be 4 amps times 5 ohms or 20 volts in series with a 5 ohm resistor. And once again, the head of the arrow is effectively in the same position as the positive polarity terminal in the voltage source. All right. So let's look at a circuit where we might actually use this. Let's start down here. So here I have a 5 amp source. Connected to a 3 ohm resistor. I'm pre-drawing some sets of terminals. All right. So we have this big ugly thing right here. How many nodes does this circuit contain? I believe it's 5 as well. How many meshes does this circuit contain? This is a little easier. Also 5. So because it contains 5 nodes and 5 meshes and a dependent source, you could argue that you couldn't use your calculator to solve this system using either nodal analysis or mesh analysis. It would require the use of a computer. So something like this would ostensibly be off limits for your exam, but I beg to disagree. Okay. So we can use the source transformation as a tool to simplify this circuit down to something that we could solve using our calculator. Okay, so this isn't going to be something that we can use all the time kind of thing. This is a special case tool for simplifying a circuit. Now, in this particular circuit, I've designed it in such a way that we could actually, with enough source transformations, convert this all the way down to a single loop circuit that we could have analyzed on the second day of class. Okay. So let's start. How many practical sources do we have? I would argue that we have 3. What's stopping that dependent source in parallel with a resistor from being treated as a practical source? Absolutely nothing, okay? So anytime that we have a current source in parallel with a resistor, we have a practical current source. Anytime that we have a voltage source in series with a resistor, we have a practical voltage source, okay? So let's start by manipulating the practical current source on the left. All right. So I've drawn these terminals the way that I have because how I like to do this is effectively I disconnect our practical source, transform it into its opposite thing. So in this case, we're going to transform a current source into a voltage source and then reconnect it at those terminals. So the terminals help me to understand exactly where I put the new thing in, okay? So if we were to disconnect the 5 amp source in parallel with the 3 ohm resistor, what is this electrically equivalent to? $15 volts. That's 5 amps times 3 ohms. And then what else do I do? And 3 ohms in series. So have I got the polarity of my voltage source correct based on the direction of my current? Yes, okay. So I'm going to disconnect that practical current source, and in its place, I put in my transformed voltage source. So what did that do? Did a couple of things, okay? Number one, it introduced a node, arguably bad. It eliminated a mesh, arguably good. One thing that isn't super obvious here is that now that 3 ohm and that 4 ohm resistor can be combined, where previously they could not, okay? So because it changes the position of resistors, it can enable resistor combination techniques to be employed for simplification where they couldn't have otherwise been used. So in this case, we have a 3 ohm resistor in series with a 4 ohm resistor. What's that going to look like? 7 ohms. So I'm going to erase this 4 ohm resistor. I'm going to make this a 7 ohm resistor here. And I got rid of that node I just created by combining those resistors. Okay. Now, technically speaking, we are at a point where we could solve this using nodal analysis or mesh analysis now, because we have 1, 2, 3, 4, still 5 nodes. If we chose our bottom node as ground, we could say that the top left node was just equal to 15 volts. Effectively, we don't need a real equation for that. We've definitely got it down to 4 meshes, which for some of us, that's enough for us to handle with our calculator. But let's keep on going just for the sake of argument here, okay? So now I'm going to transform that practical voltage source on the left back into a practical current source, because that's going to allow me to put that 7 ohm resistor in the top left in parallel with that vertical 7 ohm resistor, right? So just so that we're on the same page, $15 volts in series with 7 ohms. Transforms to 15 over 7 amps. In parallel with 7 ohms. So once again, I know this is tedious. I am going to completely disconnect. Why is it zooming? Yeah. I'm going to completely disconnect my practical source and replace it at the terminals with my transformed source. So there's 7 ohms. Here is 15 over 7 amps like so. And now I can see that the 7 ohm resistor is in parallel with the 7 ohm resistor, which looks like half of 7 or 3.5. And then I would actually do a source transformation again here. Just because my goal at this point is to show you that I can make this look like a single loop circuit, right? So 15 down here. In parallel with 7 over 2 is going to look like 15 halves in series with 7 halves. Okay, so I'm done messing around with the leftmost practical source. We've done 3 transformations at this point, eliminated a couple of nodes, a couple of meshes. Let's see, we have 1, 2, 3, 4, still 5 nodes, but we're down to 3 meshes. So let's look at that practical current source on the top, okay? So this is what I have. Let me make sure I get that direction right. Yep. So what I'm going to see between those two terminals is a dependent voltage source in series with that. Is it 7 or 17? 17. Sorry about that. $17 ohm resistor. So I'm going to put my positive polarity where the head of the arrow is, my negative polarity where the tail of the arrow is. So what's my voltage source going to provide here? What's 3Vx times 17? 51 Vx. Nothing fancy, just simple multiplication. The voltage is going to be equal to the current times the resistance, whatever those things are, okay? So I'm going to eliminate this guy up here. And lastly, we're going to perform a source transformation on the rightmost practical current source. Okay. So hopefully we've established the rules enough now to where I don't have to show you exactly what's going on over and over and over again, since we've done it at least 4 times at this point. So what should my 9 ohms in parallel with 1 amp turn into? 9 volts in series with 9 ohms. Sorry, let's make that ohms. And after several steps, this is just a single loop circuit that once again, we could have analyzed on our 2nd or 3rd day of class. Okay, no need for nodal or mesh analysis or anything like that. All right, so how do you guys feel about the concept of source transformation at a minimum of going from a practical current to a practical voltage or vice versa? Jake.
So would it be a fair technique on an exam to look at a circuit and go, okay, can I do these practical transformations in Square before trying to analyze it?
Yes. So if you look at a circuit, I would argue what I'm about to show you, which is called the maximum power transfer theorem. If you have a practical source representation of a large chunk of circuit, it will make the calculations that go into determining the maximum amount of power that can be delivered to a particular load resistor much, much easier than considering the circuit as a whole, okay? That being said, the way that I've just shown you this technique is more useful for making a complicated circuit reduce down to something smaller that you could more easily apply circuit analysis techniques to here, right? So 3 source transformations ago, we had this in a place where we could have used nodal analysis or mesh analysis to solve it. I would argue it isn't entirely necessary for us to go and break it down into its absolute smallest form like this. How can I put this? This technique is absolutely useful, and we're going to get a lot more use out of it when we get to the steady state sinusoidal portion of our class, which is the last third of the class, where we can't really use nodal and mesh analysis as much as we are going to rely on it over the next couple of weeks, because our calculators are incapable of solving systems of equations that involve complex numbers, okay? So this is something that I'm introducing now in DC circuits that we are not going to get a whole lot of use out of until the later parts of the class. You could argue superposition is the same way. Unless I'm specifically asking you to do it, you're probably going to try to figure out how I can use nodal analysis or mesh analysis, okay? This concept of source transformation lends itself arguably well as an introduction to the topics that we're going to cover immediately when we get back from the break, which are called Thevenin and Norton equivalent circuits. What Thevenin's theorem and Norton's theorem allow us to do is effectively replace any circuit with a practical voltage source representation or a practical current source representation, but it doesn't rely on just using source transformations to get there. So in some cases, it can be faster to just find a Thevenin equivalent circuit using those techniques than it would be to do multiple source transformations back and forth to make it break down into a practical voltage source or practical current source representation. If I were in charge of the material that is covered in this class, I wouldn't actually do this lecture at all. I do Thevenin and Norton equivalent circuits, maximum power transfer theorem from there, and then point out that Thevenin and Norton equivalent circuits are source transformations of each other, and we wouldn't have gone through all of this. But I don't have that level of autonomy just yet. So you guys have to suffer through one, in my opinion, annoying homework set. It's not unuseful, but yeah, I'm not a big fan of it. So that's my 2 cents. All right, so maximum power transfer theorem is something that I think is fantastic, okay? And it relies on us being able to represent a larger circuit as a practical voltage source or a practical current source. So let's say that we have the following circuit, and we'll derive it for a practical voltage source, and then we'll use these results to figure out what would happen if we had a practical current source. All right, so the power that is absorbed by our load resistor here can be expressed in multiple ways. Okay, so the first way that we could express this power is simply the product of VL and IL, which you all should be familiar with. We could also express it as VL squared divided by RL, or we could express it as IL squared multiplied by RL. So let's use that third representation because it's probably the easiest thing to do here, okay? So IL in this case is going to be exactly what I believe Hannah McPherson told us it was a couple of minutes ago. Simply VS divided by RS plus RL. And from here, the power delivered to our load resistance by our practical voltage source is going to be VS divided by RS plus RL quantity squared times a factor of RL is going to look like VS squared RL divided by RS plus RL quantity squared. So here I'm going to make a little graph. And this is going to be PL as a function of RL. And it's going to look something like this, where way over here, we have RL is equal to a short circuit, so no power is delivered to it. The voltage drop over it would be 0, therefore p squared over 0 is going to give us 0. And then way over here is when our load resistance is effectively an open circuit. Okay. And then everywhere in between is every possible resistor value that exists between 0 and infinity. Okay. Now this is a parabolic-ish shape. If we manipulated things here, which we absolutely could, we could use a quadratic equation to figure out things. I'm mentioning that specifically because you're going to be asked to do just that on your homework, okay? So this relationship right here is going to show up in your homework sentence, okay? So one thing that I'd like to point out, though, is that let's say that this peak value of the power was 100 watts, okay? There's going to be exactly one value of RL that causes this circuit to deliver that peak value. But if we came down here to, let's say, 50 watts, there are two resistor values that satisfy this constraint. Okay, there's going to be one that's lower than our peak resistor value, and there's going to be one that's greater than the value of the resistance that gives us maximum power transfer. So this is another thing that we can use to figure out if we were trying to design a power system and we wanted to figure out how to make it hit a particular absorbed power, unless we are specifically looking for maximum power transfer, we have two options. So just something to point out. Okay, so we have this equation that I've circled or boxed in orange. Let's solve for the value of RL that will make P its maximum value. Okay, so how are we going to do that? So we have effectively here PL as a function of RL, excuse me, is equal to VS squared times RL over RS plus RL squared. I want the peak value of the power. So how do I find the peak value of a function? Take the derivative and set it equal to 0. Absolutely correct. Yeah. So we're going to use the quotient rule, which, because I knew we were going to use the quotient rule, I took the time to Google what it is because I don't use it often enough to remember it. So the quotient rule says that if we want to take the derivative of a function f of x over a function g of x, that is g of x times the first derivative of f of x minus f of x times the first derivative of g of x divided by g of x squared. So f of x is going to be vs squared times RL, where x in this case is RL. And g of x is going to be RS plus RL squared. Okay. So the derivative with respect to RL of PL of RL is going to be our g of x term, RS plus RL squared times the derivative of our f of x term. So what's the derivative of VS squared times RL with respect to RL? VS squared, easy peasy. Then we're going to have minus VS squared times RL. And now I need to do the derivative of my g of x term. So how am I going to do that? Chain rule, absolutely right. So all right. And then the derivative of the inside is just 1, right? Yeah. And then this is going to be over RS plus RL to the 4th power. So let's play around with some things here. RS plus RL squared is going to look like RS squared plus twice RS RL plus RL squared. All of that will be multiplied by VS squared. Did I expand that out correctly? I think so. And then we are going to have, let's see, minus, so let's throw a 2 out here. So I'm going to have RL times RS. Let's see, so 2. And then RL squared. And then a VS squared terms goes there. And this is all over RS plus RL to the 4th power. I feel pretty confident about my ability to do algebra on that first bit because it's simple multiplication. Please let's check things for the second bit or this is going to go horribly awry. Okay. So I multiplied the quantity RS plus RL times RL, which gave me RL RS plus RL squared. Then I multiplied that by 2. Then I multiplied that by VS squared. Anybody see any problems with my algebra on that term over there? All right, so it's probably one step too many here, but just to cover my butt, I'm going to have VS squared times RS squared plus VS squared times twice RS RL plus VS squared times RL squared minus VS squared twice RS RL minus VS squared times 2 RL squared all over RS plus RL to the 4th power. If I expanded all of that out correctly, which I think I did, this term and this term go away. And then this term goes away if we stop scrolling on my screen, eliminate that too. Anybody have any problems with that level of algebra canceling stuff out? Nobody is saying that I screwed up. So, yes, ma'am.
And the step above that, we got RL squared. Where did you get RL squared from?
Which of the two RL squareds? The one on the left or the one on the right?
Right. R-
Yeah. So when I multiply this RL by the quantity RS plus RL, I get, yeah. Yep, no, not a problem. I would rather make sure I get the algebra right so that the result comes out correct than have to hand wave and be like, I screwed up somewhere. This is what the result is supposed to be. So. All right, so let's simplify this down one last time, and then we're in a position to look at it. So I have a common factor of VS squared that I'm going to take out here. I have an RS squared minus an RL squared over RS plus RL to the fourth power. So we set our derivative equal to 0. So under what condition will this be equal to 0? Now, because it's a fraction, we only need the numerator to be 0, right? So let's simplify things ever so slightly and say, under what condition is the numerator 0? So if VS squared were 0, the power is 0 because the whole system is 0 effectively, right? If we don't put an input voltage into this thing, everything is going to be 0. So that is a solution, but it's a trivial solution. So what was the other one, Tyler? Okay, so the quantity in parentheses has to be equal to 0. So what condition works there? Okay, so what happens if we were to take the square root of both sides? You're nickel and diming me here. When RL is equal to RS, we have maximum power transfer, right? Because we don't have negative resistances. Okay. So this is our condition for maximum power transfer to occur. When RL is exactly equal to RS, maximum power transfer occurs. Effectively, we have, for those of you who are going into electrical engineering, later on, we have a matched network here. And that matching is what's causing maximum power transfer to occur. So let me write that down. Maximum power transfer occurs when RS is equal to RL. And then from this, we could say that PL max. So let's look at our equation up here, just so I don't mess this up. So VS squared times RS, where we're replacing RL with RS, divided by RS plus RS squared is VS squared times RS over 4 RS squared is 1/4 VS squared RS. No, excuse me, divided by RS. My apologies. Stop erasing. Don't know why that up there. Okay. So that is our equation for maximum power transfer. by a practical voltage source. So what do you think would happen if we had a practical current source? Well, for a practical current source, we know that I would be equal to Vs over Rs. So that's going to be 1/4 Is squared multiplied by Rs. Simply by using the concept of electrical equivalence without any additional work. All right, so let's put this into practice and then I will be done ranting about circuit related stuff for the day. You guys won't have to hear me again until literally the next year. Okay. So let's say that we have the following circuit. We have a 3 ohm resistor connected to a 12-volt source. A 6 ohm resistor connected like so. 7 ohm resistor connected like so. And here is our load resistance. Okay. We want to know two things. Number one, what value of RL will cause the remainder of the circuit to deliver maximum power. And number two, what is the value of the maximum power that can be delivered? So effectively, what part one is asking us to do is to convert everything that isn't RL into either a practical voltage source or a practical current source. Once we have a practical voltage source or a practical current source connected to just RL, then we can simply figure out what that value of RL is and use our equation. Okay. So you guys tell me how I'm going to convert this circuit into either a practical voltage source connected to RL or a practical current source connected to RL. Okay, so the 12 volt and a 3 ohm resistor could be converted into 4 amps and 3 ohms in parallel. All right. So here's step one. 4 amps in parallel with 3 ohms in parallel with 6 ohms. There we have 7. Here we have RL. So what's next? So what's 3 and 6 in parallel? 2. What next? So we want to leave RL alone, right? We don't know what RL is, so it's hard to. So convert our practical current source into a practical voltage source. So that would be what? So 8 volts. 8 volts in series with 2 ohms. Sorry, that 7 looks too much like a 2. All right, what now? All right, so 2 in series with 7 looks like 9. So am I done? Why am I done? Because I have a practical voltage source connected to RL, okay? So the answer to question 1, what value of RL causes maximum power to be delivered is RL needs to be equal to 9 ohms. Absolutely correct. For part 2, I now apply my equation, right? So P max is going to be 1/4 times Vs, which is 8 volts squared, divided by RS, which is 9 ohms. So that's going to be 64 over 36 watts. And that could be simplified, but I'm lazy. 32 over 18. That's it. So this concept of practical voltage sources and practical current sources, and what we're going to be doing with them in particular once we get back from the break, Thevenin and Norton equivalent circuits, allow for pretty straightforward power analysis, right? Where we don't need to understand what's going on in every individual part of the circuit. We just need to understand how it behaves as an equivalent circuit. And then from there, our power calculation is pretty straightforward, right? So imagine if you were trying to figure out what value of RL would cause maximum power transfer to occur without using that simple representation. It would be nearly impossible. It would take hours of trial and error. Whereas with this practical voltage source representation or a practical current source representation, power relationships are rather trivial, okay? All right, so that is enough ranting out of me for the day. Work on your in-class assignments. I'll be happy to help if anybody feels they need any. And if hopefully I won't see any of you guys after today, so have a great break and all that kind of jazz. I'm not saying don't show up to my office hours or anything, but we both know tomorrow afternoon, everybody's checked out.